introducing spherical CNNs. So, convolutional neural networks have already shown promising results for 2D image detection and classification. They have been providing very accurate results without significantly large computation time or power. But with the growing use of omnidirectional images for drones, robots, autonomous vehicles, or even for like research problems like molecular regression problems, or even global and climate modeling, we need to modify the convolutional neural networks so that they can handle spherical images as well. This is just like an example of an omnidirectional image. The left image, I mean, the figure 1 was basically taken from a 360-degree camera. It's essentially a CCTV camera. And the second image is a 360-degree panoramic shot. So this is just an example to show what kind of images we are talking about here. So the problem with like normal CNNs is that we can already see if we like in this figure, say an image is being projected on the sphere, and we are considering only the highlighted region which lies on the equator. We see that the like if we project this sphere on a plane, then the highlighted region would stay the same, provided that this highlighted region is on the equator itself. But if we rotate the sphere I mean in any direction, then the projection introduces sort of a radial distortion, I would say.
Hello? Hello?
Yes, I'm sorry. I think we lost the audio connection.
Okay.
Yeah. So basically, what we're trying to say is that the same region on the same sphere, where the sphere is oriented differently, which is the right-hand part of the like the figure 3. Then the project, when we project the sphere again on a plane, it looks nothing like the sphere. So nothing is preserved, and it is very difficult for a traditional 2D CNN to detect regions on a spherical image. This is again an example where we just try to show the problem with normal 2D CNNs. In all of these images, say if we try to build a classifier, I mean a network which tries to identify Antarctica. In all of these images, Antarctica looks different. So a traditional CNN would fail to identify Antarctica. So now moving on to the solution. So if a square grid of pixels has discrete translational symmetries, no perfect symmetric grids for the sphere exist. So this means that we cannot define the rotation of a spherical filter using a single pixel. Now, SO3 is a 3-dimensional manifold. So a naive implementation of SO3 correlation is in the order of n to the power 6. That is, if you consider the set of all table I mean, if you consider the set of the table of all possible rotations of the sphere, then there is something. I mean, then the order, the order of the entries in the table would be very large. Again, in 2D CNNs, we detect some sequence of pixels with a invariant being translations. But in spherical images, the invariant we want to preserve are rotations. So before we move on further, I would just like to mention that this is more of a theory. I mean, our work is more of a theoretical review of say spherical CNNs. Although we have implemented this practically using PyTorch, but we do not have like a eye candy sort of thing to show for visualization. So we would concentrate more on the theoretical side. And before we move on, we would just like to introduce some notations for the audience. So the first one being the unit sphere. So it's nothing but a sphere with radius 1, and we will be considering images defined on it. The next would be spherical signals. So we model spherical signals and filters as continuous functions. So it would be essentially a mapping from S2 to RK, where K would be the number of channels. And thirdly, rotation group on a sphere. So the set of rotations in 3 dimensions is called iso3. The spherical, which is also known as the spherical orthogonal group. Rotations can be represented by 3x3 matrices that preserve distance. So the norm of Rx would be equals to X, and orientation would also be preserved. That is, the determinant of R would be equals to +1. Also, it can be verified that this SO3 is a group. It can be verified in the sense that composing 2 rotations result in another rotation, and every rotation has a unique inverse rotation. Also, the identity map satisfies the definition of a rotation. Again, the set of all rotations is a group under composition. So, but because rotations are not commutative, it would be a non-abelian group. Furthermore, the rotation group has a natural structure that makes it a manifold for which group operations are smoothly differentiable, which makes it a 3-dimensional manifold and also compact. Next. So let us define the rotation operator LR, which takes a function small f and produces a rotated function given by LRF. This is done by composing f with the rotation R inverse. So equation 1 defines the operator. Now also the volume of some spherical height map does not change when we rotate the sphere, which gives us the following identity. So essentially this integral calculates the volume of the spherical height, and regardless of whether the rotation operator is applied on X, the input, or not, the volume remains same, so we get the identity. So this also means that the rotation operator is a unitary operator which preserves dot product, is normal, and perhaps preserves orientation as well. So from the previous slides, we had equation 1 and 2, and we prove that the inverse of the rotation operator is adjoint to the rotation operator itself. Yeah, these 2 equations is the proof, basically. Using 1 and 2, we get this small proof.
Avirup, if you don't mind, I would like to just look at the earlier slides.
Yes, ma'am, sure.
This means that the rotation operator, which is LR, is
Yes,
unitary. Okay, preserves dot is normal. If you say is normal, you don't have to say unitary. And preserves, if you say unitary, you don't have to say one
normal.
Yeah, you say unitary, it is normal. Preserves orientation. What do you mean by preserves orientation? So you mean that if you apply LR to some R prime of F, then that is same as LR of F. Is that
ma'am, can you repeat it again?
What do you mean by preserves? What do you mean by LR preserves orientation?
So orientation is yes, ma'am. So here orientation basically means that, for example, if for in a picture, if there is one left and right, so even if you rotate it, the left and right does not changes. I mean, it remains same.
Determinant wise, right?
Yeah.
We mentioned this in the previous slides as well. Just
so
go back maybe
once. You're saying that if determinant of
determinant
is the magnitude of the determinant will not change.
The magnitude of the determinant. More than magnitude, we want the sign of the determinant to be +100. sign of the determinant. Okay, all right, go ahead.
Yeah, so we get this proof, and uh, for rotations on the sphere, we compute correlations as an inner product between the input feature map and a filter rotated by some rotation R in SO3. So also to give some intuition for this, on 2D surfaces, the correlation, which is the measurement of the similarity between two signals, is computed by finding the inner product between the input feature map and the filter shifted by the translation. So the spherical correlation is defined as this phi star F over R.
Yeah, please don't go ahead. I need a moment.
Yes, ma'am.
So you're saying for rotations on the sphere, we compute correlations as a product between the input feature map.
And the filter also is rotated.
What do you mean by the input feature map? Oh, just the image.
Yeah.
Input feature map could be, ma'am, like image or an image like which has been on this some convolution. This correlation is already applied. So yeah.
Okay. So and a filter rotated by some R. In a product between input feature map and a filter rotated by Oh, we compute this as the product between these, and then you rotate by some R. Is that what you're saying?
No.
Let me just read that equation maybe. So the correlation between the psi and F, where psi is probably your
Size of filter. Yeah.
And how do filters look like, by the way?
So, ma'am, so in case of so there are this, I mean, so this is we'll discuss it in the further part of the slide, but there are so actually I mean, we will define in the next slide we'll define something called this as yeah. I mean, I will come to that, but it will be defined.
Okay, so psi is a filter, and how are you correlating with F? So it is defined by its action on some R in or action on R in SO3 as in a product LR comma F. So LR.
So we apply the rotation on the filter, and then it's the inner product between that and F.
Sorry, I mean, taking a while to get this. So
Yeah.
LR is the map from where to where. Just
so, ma'am, you can assume it like this. Let's say this F is a spherical image. So this the filter here is filter here is also will also be a sphere. So you can think of it as like the so F is like inner sphere, and there is this phi is another filter which is directly above this F spherical image. So it is basically like a ball which is enclosed inside another ball. So yeah, it's like two ball. I mean, a ball.
No, that is fine. Yeah. I got. No, LR as a map. It is applied.
This is a rotation operator. Simply, it just rotates because this phi will also be a sphere. I mean, that's what I'm trying to say. So in case of CNN, we have this small small matrix of 3x3. But in case of spherical CNNs, or in future that we will call this SO3 convolution, so the filter will also be exactly same as the size of the spherical image, and we will just instead of just shift. So in regular CNN, we just shift the image. We just translate the image over the whole grid. But in this case, the filter will like cover the whole ball, and we will keep rotating the filter over the image. So that's what we are trying to do here.
Okay. So let me just get things right. So LR, the domain of LR is just
so LR is like so, ma'am. So LR is just an operator which does this rotation. So the R comes from SO3. So R belongs to SO3. SO3 is a group.
So yeah, okay. So this is an operator from SO3 to itself. Okay.
Yeah.
And now you have this inner product between LR and F. LR of some C and F defined as integral over S2. So summation psi k.
we have just expanded the definition of this LR and sigma, but this is actually in case of normal images, we take that 3x3 matrix, we put it on some part of the image, and then we multiply all the things and add that thing. So this is exactly the same thing, but with the spherical.
So your
filters.
K is probably going to vary over pixels, right? Pixels.
Yeah, it's basically the filters, the different filters that we have.
Yeah. So the implementation we're going to discuss later.
No, but I just want to understand the notation. Your K varies from 1 to capital K means what is your F suffix?
Yeah,
K,
so you can think of it as like so when we are taking this spherical this, let's say, spherical kernel, the spherical kernel or filter phi. So anyhow, like when we are doing this sort of multiplication, we have to like fix the number of points at which we will evaluate that thing. So it is just that. So it is just that.
Okay, so for now you want to keep that capital K unknown, but
yeah, but ma'am, actually this is just for the definition, but we will do this whole thing in the Fourier domain anyhow. So
all right, so let me just take a note of this correlation definition. This is just inner product LR, and you have written the same thing here. Yeah, same thing. Okay, all right, please go ahead. It will take me a while to this is all new, so just bear with me. I'm not testing you. I'm trying to understand.
Yes. Because this is just this is simply this group theoretic formulation of the convolution neural network that we have studied. So,
yes.
So all of the operations that were defined there, it's sort of generalized in this group theory.
Okay.
Yeah. And this, like Ayush has already mentioned, this would be implemented in the Fourier domain actually. Yeah. So now, ma'am, you have something to say?
No, I said please go ahead.
Okay. So now we move ahead with proof of equivariance. So in deep learning, general equivariance is more useful than invariance because it is possible to determine if which features are in the right spatial configuration if they are invariant. So we need to show that equivariance is maintained in the correlation between the signal and some rotated filter, which is important because we want to establish that in a rotated image, we are still able to detect the same object. So now we define what we mean by equivariance. So a function f is equivariant under some group G if for a given transformation G in a capital G, f of G of x is equals to some G dash fx. Also, G dash is different from G. This implies that the function applied to an input which is being transformed by an element of the group is equal to some other transformation in the group. But this is applied to the output of the function with an unmodified input, basically.
Will this show this whole thing with an image also?
Yeah. Next. Yeah.
Just in your definition, did you have a superscript on it
also? No.
So,
this was my cursor.
So yeah, this image essentially helps us distinguish the difference between invariance and equivariance. The left-hand side image, when this image of the cat is shifted by some S, the output is the same. Whereas in equivariance, although we shift the images, the output is also shifted. So this is what equivariance essentially means. So now we would just like try to highlight the proof of equivariance here. For more detailed proofs, we would refer to the original paper here. So correlation has been defined in terms of the rotation operator LR, which acts naturally on the input space of the network, which is like spherical images. Now to justify using it in the second layer of the network and beyond, we need to show that this operation is equivariant. And hence
so before we move on this thing, so basically in this whole convolution neural network thing, so there are basically three type of layers are, so this convolutional neural network is just composed of two things. One is this whole convolution type thing, and another is a fully connected network that is more like this multi-layer perceptron thing. So this simple CNN, the CNN layers are basically the combination of this equivariant and the invariant layer. So when we are generalizing this terms, when we are generalizing this notion of convolutional neural network over not just the translation symmetry, but any sort of symmetry. So we want to define the sort of equivariance and invariance over that. So in general case, the convolution layer in the regular CNNs are the equivariant layers, and the pooling layers that we generally use, it is the invariant layer. So with this whole problem is simply learning this sort of equivariant representation. So
repeat yourself once. What do you want as equivariant and what do you want as invariant?
Yeah, ma'am. So in regular CNN convolution neural networks, that what we have already studied. So in those CNNs, so the convolution layers that we have, it is basically the equivariant. It is the equivariant layer, and the pooling layer that we have, it is the invariant layer. And with the, so if we think from the perspective of learning, in the convolution layers, we generally learn this weights of this kernels. So in this group theoretic means we simply it means that we are sort of learning this equivariant representation. We are learning these functions, like, so in this image, and we say this f. So s is definitely the group action, so that is already there. But this f, which is sort of giving us this equivariance. So we are learning that. So this is that is kind of observed.
So you want to learn the equivariant. You want to learn the
equivariance because
the correlation has to be equivariant.
Yeah. So if you're working with any group, so the whole idea of this convolution neural network is that learning the equivariance for that particular group. In regular cases, it was the translation group, so we were learning that translation invariance and the translation equivariance basically.
Yeah, and it is like also important because like for the later layers also, if we want to put convolutional networks, we want it to be equivariant, since essentially we are just like learning feature maps. So it's essentially a mapping from this R3 to some higher dimension, like it's some spatial mapping. So we would want.
Yeah, it is clear that you would want that commutative square to hold throughout all the layers.
Yes.
The commutative square that you showed before, commutation relation, you would want that to hold throughout the layers. That is the point, right?
Yeah. So
on the previous slide, there was a commuting relation. That's what equivariance means. That relation you want to hold.
Basically we want to learn this f function. We want to learn this f function because s is already defined by the choice of group that we have. So we just want to learn what the f will be for the particular group, or for the particular data set, not the group but the particular data set.
Okay.
Yeah. So here is the proof of equivariance for the correlation that we have defined in the previous slides.
So I'm like, so this is like simple thing. So we'll not like go through line by line, but it is, it is proved in that way. So we will.
So just give me one moment. So this, see, LQ of f is f of q inverse. That is true. And why is this phi of r inverse? Okay, never mind. Okay, I will go through this later. Please go ahead.
So the next thing that we want, again, to like justify using these layers in the next, from the second layer onward in the whole network, we are defining this composition operator. Hello. Yeah. So we are defining this composition operator as CV f of g, which is the composition of v and f on g. Again, this acts on functions by post-composing them with v. Now, since the left transformation operator L acts by pre-composition, C and L commute, and that is what we have shown in the next line. And the rectified feature map inherits the transformation properties of the previous layer. So, say if we have convolutional blocks in a particular network, each block say has two convolutional layers followed by a pooling layer and then some non-linearities. So here we are trying to show that the non-linearity is being passed on through all these blocks.
Yeah, and also like when we apply this non-linearity, I mean between the subsequent convolution layers, in between the convolution layers, this equivalence that we were already holding, it will not go away. That will still be preserved. So that's the whole point of training the pointwise non-linearities in this case.
And finally, we would want to show the same thing for pooling. The non-strided max pooling operation applied to a feature map F, which maps G to R, can be modeled as an operator P. Again, this is like a new operator that is being introduced here just for the sake of explaining things. Now, P acts on F as follows. So it's essentially the max of Fk, where K is varied over Gu, and Gu is the G transformation of some pooling domain. And
basically a coset.
Yeah, it's a coset.
So you want to say first of all why a pooling domain is a subgroup, right? Because
so ma'am, we are saying so we are basically saying that in this group theoretic formulation, so pooling can be when we want to do the pooling, so just to like reduce the dimensionality itself. So there are two ways to achieve that pooling. So maybe we can go with a subgroup as well as the coset. So that is like the describing this. There are two ways to achieve that same thing. So yeah.
So like since pooling tends to so pooling is essentially like reducing the variation in a feature map, and hence it makes sense to subsample the pooled feature map.
No, that is fine. That is fine.
G some
element G element. Some
yeah.
Okay. Yeah. So you take some coset of U. First of all, okay, it might be there somewhere that this you have to probably take some subgroup. Not probably. You have to take some subgroup of G, and then you define P of. So this P is dependent on G, right?
The P we are this particular G. No, so that is
no, P is not dependent on G. P is the operator, like the pooling operator.
Who is the pooling operator?
So that is like predefined.
Okay. So, this is getting applied on G. I see.
Yes.
So you define this on the group. So P of F sends a group element to the max of F case where K belong to G. So this is what I was asking. So feature maps, you are considering them as maps from G to R.
Yes.
So this.
And since there could be like multiple features, so so for each filter will be like from G to R, but since that there can be like more than one filter, so there is it's not an issue that we are just restricting ourselves to R1. I mean, if by taking the K maps, we can. I mean, by taking this K filters, we can get this RK representation. So that is there.
Okay, please go ahead.
Yeah. So in a standard convolutional network, pooling with the stride 2 is the same as pooling and then subsampling on this H, which is the ordered pair 2i, 2j, where i, j belongs to two-dimensional. I mean, the I and j are integers basically. So this is a subgroup of D equals to Z square, Z2. And in a regular convolution, again, U is usually 2 cross 2 or a 3 cross 3 square, including the origin, and G is just the translation. Also, the paper has elaborate proof that pooling commutes with LH. So P LH will be equals to LHP, and we can obtain full G equivariance by choosing our pooling region U to be a subgroup this H that I already spoke about. So this feature map that results from pooling over cosets is invariant to the right action of H, because the cosets are similarly invariant.
So
in this case,
so from the intuition perspective, I just say that like in this case, this particular when we want to do this pooling, so so what basically we use is that we take a group. So I mean in a group, like all infinite type of rotations are possible, the SO3 group. So the subgroup that we will be taking is the group where each thing is rotated by the 60 degree. So that will be the subgroup. So now when we want to do this sort of max operation, we are restricting ourselves to that group when in which the first rotation, it is the identity, then it is rotated by 60 degrees, and the same goes on. So there will be only 6 elements in it. Yeah, because once you do
first of all, this means that the U in the beginning was not necessarily a subgroup. So you take some subset of
no.
First thing.
No, but no, the subset that we are taking, it should also have a group structure. So when I'm taking the 60 degree thing, so again, so even if you combine two rotation in that subgroup, so which is basically in which each element rotates. So each rotation matrix is just it only consists of rotation matrix which corresponding to rotation like 0 degree, 60 degree, 120 degree, 180 degree. So even if you combine even if you like just take a composition, we will again get the rotation matrix which is like which is like the rotation by 60 degree into k times.
I understand. So you want to take a subgroup that's at the end. Right? In the end, you are saying that the pooling over cosets is invariant because the cosets no, not there. You can obtain full G invariance by choosing the pooling region U to be a subgroup. So in the above what you have in the first bullet point, it's a more general definition where U is not necessarily a subgroup. That's the first remark. The second remark is that so for practical purposes, is your G Z2 even here, like not in the regular thing, but even here is G Z2?
No, so that is just an example.
Yeah,
I mean,
authors also the first comment is definitely general, but it does not guarantee the equivariance. So
no, that is fine. No, that no, that is fine. No, I'm asking you, what is your G in the end?
So G is the base. G is the group that you're working with, the SO3 group in our case, spherical CNNs. So whatever the subgroup.
So always one has to think about SO3, right?
Yeah, in this case, yeah. Okay.
So
yeah, but this proof is being done for a general group.
That is okay.
But the only thing is that we want equivariance. We want equivarience throughout the network, so that's where we are restricting ourselves to subgroups.
That is also fine. I just wanted to know what G I should be thinking about all the time. So G,
in case of spherical images, it has to be SO3. But
SO3.
if we are working with some other, when we want to like record like some other sort of symmetries, say reflection or something, in that case it might be something different. But it will again depend on the type of symmetry or equivariance that we want. So in case of a group of reflections, that will be different, or any other group.
See, but for now, for the spherical CNNs, you are looking at SO3.
SO3, yeah, that is
SO3.
For
spherical
CNNs, yeah, that is all I'm asking. Yeah. Okay, go ahead.
Yeah. So yes, ma'am. So now so this is just for the theoretical purpose. This is fine, but now we have to like actually apply this thing. So it usually these methods are good for the proof, but not for the practical implementation. So we have to somehow move to we have to somehow make sure that these things are we can do that. So even to do that, let's just first
so to just a moment, to sum up what you have done so far is you have modeled the correlation operator, the correlation as an operator, right?
Yeah.
Then you did max pooling as an operator.
Yeah.
Correct.
We basically defined this convolution. So yeah, there is one also, there's an issue in nomenclature. So whenever these in this neural networks and all these things, whenever we mention correlation, if we observe the operator, it's actually the correlation operator. So I mean, the machine learning people have just started to call it correlation. It has become correlation, but in correlation, we take the filter and we rotate it by 180 degree and do that. But in the regular
that is
CNN
okay.
thing,
That is
yeah.
okay.
So yeah, so
No,
I
I'm just trying to see up till now, what are the different parts of a CNN that you have modeled as operators. One,
yeah.
you have modeled a correlation as an operator. You have
Yes.
modeled this max pooling as an operator.
Yeah.
And what else? There was one more.
The non-linearities.
The non-linearities. Yeah, we find that key even when we
Correct.
apply this
So-
non-linearity, we still have that equivalence.
So these three things have been modeled as operators on the set of feature maps.
Yeah.
Feature
Basically, I
maps
mean,
from
describe
SO3 to R.
these component of the CNNs for a general group, or in this case, the spherical, this SO3 group. Yeah.
Right.
Yeah.
Okay.
So yeah, so the idea is so yeah, so again, so when we want to do this convolution or correlation over the sphere, so we have to basically take the kernel, and we have like, so there are actually two ways to do this. There are two ways to do this sort of this taking this correlation operator. The first operator, you can, it's called actually S2 correlation, in which we take a we basically take a sphere and we define a small filter. It's exactly like what we do in regular CNNs, but instead of rotating, yeah, and we do exactly the same thing. We take a small, let's say 3x3 matrix type of thing, and I mean, I'm talking in terms of computation, and we rotate, we set the line, we mark the lines, latitudes over the sphere, and we rotate that whole matrix over the sphere. So that is called the S2 correlation. And there is another way to implement this thing. Is called the SO3 convolution or SO3 correlation. In that case, what we do, we take a spherical image, and we take we take a spherical kernel. We just put both things on each other, and we keep rotating the spherical kernel. But the problem here is that, like, there are infinite number of points where these things can be evaluated. So how to restrict ourselves to that? So the idea is we will move into this Fourier domain. I mean, not exactly the Fourier domain, but I'm just using the name for the analogy. We'll move into this thing, and we will use this convolution theorem for this particular space, so that we can do this element-wise operation, and we can get away with this whole rotating the kernel over the whole domain. So let's start with the spherical harmonic. So it is basically the set of function which can be used as a basis to represent any function over a sphere. So it is a high dimension. It's a high dimension. Just one second. It's a video laptop. Yeah. So so it's basically the high dimension analogy of the Fourier series, which is the complete set of bases for the periodic functions. So I mean, let's see like how this let's see like why we are, how these things even come up. So what we simply do is we take the Laplacian operator, and we describe that Laplacian operator in terms of spherical coordinates. Why we started with the Laplacian operator in the first place? So the Laplacian is basically the if we apply this Laplacian operator at any one point, let's say in a spherical image, or at any, like, for any case, so it's basically the difference between the point. It measures the difference between let's say a point and the average of all its neighbor. So it just measures that how a particular point is different from its surrounding point. So that's what we want in case of our spherical images also, that if you are taking a point, how it is different from other, how it's different from its neighborhood pixel. That's simple that. So we just take the Laplacian operator, and we just represent it into using the spherical coordinates, and then so the Laplace equation says the Laplacian of some function equals to 0. So here f could be any signal which is defined over a sphere. So we just just to restrict ourselves to the smaller class of the function, we take the f and just decompose into this two function, one which is solely the function of radius, and another function y, which is the function of the theta and the phi. So theta is I mean, the one theta is like rotation along the yz axis, and another phi is like rotation along the x and z axis. that is that on solving this, I mean, this is simply that, and on solving this particular equation, we get something called the spherical dynamic harmonics. Harmonics, because any solution of the Laplacian equation is called harmonics, and since this is defined, this particular solution is calculated for the spherical symmetry. These are called the spherical harmonics. So these are the general basis. So these are the spherical basis for the different LNMs. So here we can see that L and M. So L is just the L and M are just the degrees and order of these bases, and these are defined in this. I mean, these are just a pictorial representation of these bases. Yeah. So now once we have defined this basis, so it's now we have to like generalize the idea of the notion of the Fourier transform also, because Fourier transform also. So the correlation and correlation can be computed very efficiently in the fast Fourier transform, as we have already seen in the class. And also this, so since we are working with spherical images, so there is a lot of symmetry in it. So we can also leverage we can also leverage the symmetry, and we can implement this fast Fourier transform for the spheres also, which is not possible for any general surface. I mean, but since sphere has a symmetry, we can implement this fast Fourier transform also. So we basically have to take our function and we have to project over these this spherical harmonics that we have shown in the previous slides. So yeah. So in case of spheres, these bases are called spherical harmonics, but in case of SO3, which is this rotation thing, we have the bases that we have, we call them the Wigner D functions. So Wigner D function, so this is simply the projection of any function that we have over this basis. That's how we do this. That's how we define the Fourier transformation in this particular domain. And for
just give me a moment to understand. If X is the manifold S2 or SO3, U prime is the corresponding basis functions.
UL, ma'am. It's UL. L is the index, yeah.
Okay. Defined as FLB. Oh, okay. So
yeah, this
simply,
is simply the projection.
Yeah, exactly. In this new basis.
Yeah, it's just written in the continuous
similarly,
fashion.
Same thing. Yeah, same thing for any kernel also. Yeah. And so essentially, you have the similar thing, right? That if you want to do correlation, then you can take the FFT or whatever.
Yeah.
This FL. FL hat and FL hat and multiply them in the other domain and apply inverse. Is that
so it? Yeah. So the idea is basically that take this Fourier transformation, and in the paper also goes on and proves that this convolution theorem that we have for our regular cases it also holds in this spherical domain also in this when we are working with S2 and SO3s. So it also holds there. So yeah. So our main idea is, so this is just some definitions here, that the inverse Fourier transform. So this is just some basic properties of it. But so yeah. So
that is okay. You will require some constant outside. That is fine.
Yeah. So the idea is that. So here we are simply saying this. So in case of S2, it is fine. But when we are calculating this Fourier transformation for this SO3, so there is another, because of the symmetry of the sphere, of course, there is some special property shows up. It says that instead of directly taking that, projecting the function over the basis of SO3, I mean whatever we have defined, this Wigner D functions. What we can do is we can take the S2 fast Fourier transformation of that particular image, and the S2 Fourier transformation of discrete Fourier transformation for our kernel, and whatever the representation that we get, I mean the Fourier the representation that we get in this Fourier space, we can take their outer product, and that will be exactly same to the SO3 Fourier transform. So in this step, what we are basically doing is that we are taking this SO3 Fourier transformation, and we are just representing it simply using the S2 correlation and this outer product. Yeah. So that's what we want to do. And once this thing is done, it's just like, yeah. I mean, so we'll get after this thing. We will. Yes, ma'am.
Ayush, I didn't understand what special property occurs. What? I completely missed it.
Ma'am, are you talking about the Wigner
so, ma'am,
functions?
actually,
So he said some special property occurs because of.
So, ma'am, so in case of ma'am, SO3, in case of SO3, the basis vectors are this Wigner D functions. I mean, the Wigner D functions mentioned here. And in case of S2, the basis vectors are those spherical harmonics. So these are two basics. So so generally, when we see the projecting over this, I mean, this Wigner D function, it's more, it's harder actually. So what, instead of doing that, we are simply using this property, and that, I mean, this property that we take the S2, we take this Fourier transformation using this F2, and whatever the representation that we get, if we take the outer product of that, it will be equivalent to taking the Fourier transformation with respect to this SO3 domain. So that is the basic idea of it.
And also, we had a relation between this this harmonic and the Wigner D function in the previous slide.
And also, and once, because that is like the more computationally expensive part, the inverse Fourier transform in SO3 is pretty straightforward. I mean, that is a closed form solution for that as well. I mean, you can directly write it. So once we done that, we do that, and yeah, we get a representation.
Okay,
so, ma'am, so this is like the theory part. I mean, now we'll show you some of the we'll show you this particular thing for the MNIST data set as well as the other data set. So first, I just tell you about the data set that we have used. So there are two data sets that we have used. The first is the MNIST data set. So it is basically the 2D. It basically has a 2D images, but what we have done is we have projected that this 2D MNIST images over the sphere. So, but because of the geometry of the sphere, we cannot project the whole image over the sphere. So the image gets projected in the only the hemisphere. So so that is our one data set. Another data set is this ShapeNet data set. So it is basically a collection of some 51,300 CAD models. So like I can show you one particular example. So these are basically the 3D objects. It's that. So it's basically the collection of this 51,000 such objects, and there are like 53 classes. So there are airplanes, sofas, TVs, and libraries, books, chairs, and these type of objects are there. So in case of spherical CNN, it is pretty straightforward because we are directly projecting the images over the sphere. So that is fine. But in case of these 3D objects, I mean, so ma'am, for this thing we have used like some of the, I mean, the author has mentioned how to use this thing. So what you can assume, like, so I'm just, because from the code it's like it's pretty convoluted to like even go what's happening. So basically what they have done is they have made a sphere outside of this particular 3D object, and then what they do is like, it's sort of, you can think of it like that from the center of this airplane some rays is coming radially outward. So whenever they hit the sphere, some reading has to be observed. So that's how it is, like this particular airplane is projected over the sphere. So that is how we are converting the 3D model into the spherical image. Now let's talk about what exactly information that we are storing there. So the first information is we are storing as the length of the length of the ray which is hitting the sphere. So for example, if there is a sphere, I can show with, I think that would be much easier because not in minutes. So for example, this is the sphere that we have, and let's say this is our airplane is there. So whenever so this is the center, so this ray goes here and hits here. So at this particular point, we store a few values. So first is the length of this ray from wherever it starts and it hits the border. So in that way, we will get, I mean, it somehow encoding the height of that particular part of the airplane, but we are just taking like it into this dual mode. We're subtracting it from the radius, so we'll just get only this height of the particular space that we are located in. Second information that we are storing is the sine and the cosine of this particular point with respect to its surrounding. So we're just storing these angles here also, and so these give us like the three dimensions. But author has also mentioned.
Sorry, so some axis has to be fixed here.
Yeah, ma'am. So with respect, some axis is fixed. I mean, so we take this angle with respect to its surrounding. So when we do that, it already fixes the surfaces. For example, when we want to take this angle, we take its left neighbor, so left side pixel, and we calculate its distance there. I mean, not the distance, but the angle. Like it basically gives us the idea that how particular point is elevated with respect to its neighborhood. So that is the idea.
So just the gradient or slope at every point.
Yeah. You can gradient that information, and but author also says that I mean, so these objects are the non-convex objects. So they calculate the convex hull of this object. So once they calculate the convex hull of this object, they get this particular sort of convex body, the convex representation of this set, and they then they calculate that this exactly the same thing, this arc length and the sine and cosine for convex hull of this body also. So that's how we get the six-dimensional spherical image. And after that, they do this exactly the same thing. So I just go over this MNIST thing. So in MNIST thing, we simply did that. We just I just come to the network part. These are the things that we have defined like verbally to you. So
should expect a length 6 vector for every point.
Yeah. For in case of the 3D objects, not in case of MNIST, it was just the one-dimensional spherical image. But in case of those 3D objects, it was a 6-dimensional spherical image. So we have to show that the spherical CNN works better than this this regular CNN. So that's what we did. I mean whenever possible. So to compare this thing, we have created this two layer feed forward neural network. This simply convolution layers and two convolution layer, including this ReLU non-linearity, and we did that, and we just simply did the one epoch of it, and we get the 95% accuracy of it. So in this case, we did not perform any data augmentation or any sort of rotation and that sort of thing. And when we did exactly the same thing with the spherical CNN also. So for the spherical CNN, the architecture is like this. So first we define this S2 convolution. So since we already told that this S2 convolution it's a bit, so there are this two S2 and SO3 convolution. So S2 convolution we have done. The authors also claim that they have just done to smoothen out the image. For the MNIST, it does not. Just to smoothen out the image. So that's the reason that it started with the S2 convolution, and after that it just the SO3 convolution layer. So in the slide also that I showed you, right, when we first do that the Fourier transformation with respect to S2, and then we take the outer product, and so that's exactly what's happening here.
Take the inverse with respect to S2.
Inverse Fourier transform with respect to this SO3 basis. Yeah. And we get the Fourier transformation with respect to SO3. Yeah, so that's what we are doing here. So the layer is kind of same. So this we first start with the So these are convolution layer. We started. So this is our first convolution layer, and this is our second convolution layer. The name Con1 and Con2, and we designed exactly the two-layered architecture, but instead of using this. In the previous case, we were using this regular CNN layers. And now we are using the spherical CNN layers. We kept everything same, and so also I just calculated this bigger network also that has like more deeper thing here. But it takes them actually a lot of time to run. So we even with the simple original, the smaller network that the author has proposed in the paper. We did that even with the single iteration, we got this 98.96% accuracy, even without doing any data augmentation. and all that thing. And now, and also this model will have this rotation invariance also, that
How
which
much
is.
data are you using here?
So ma'am, total
MNIST,
in MNIST 50,000 images. Ma'am, your voice is cracking actually. Yeah, but your question was your question was that how many images we are taking. So this MNIST already comes with this 40,000, 10,000, 10,000 split. So we are using this 40,000 images for the training, and the rest 10%, 10,000 images, I mean, for the validation and testing. So that is the default split that we have. Hello, am I audible?
How much time did the spherical CNN?
Spherical CNN, ma'am.
One epoch took around half an hour.
It took around on the CPU. I think it took around that. But ma'am, the benefit comes out of that we do not have to do any number of those epochs. I mean, so in case of
fewer layers.
We can work with the smaller networks. We can work with the less parameters, and they do that. And also in case of MNIST, okay, this might seem bit an overkill that we are taking so much time, but when we go with the spherical images, when we try to take the spherical images and project into the 2D, it does not work like that. So that's what we did in SHREC. The problem is that we just cleared. I mean, our output got cleared. So we did not have anything to. I mean, but we can include those things in our report. So for this data set, for this ShapeNet data set, we got like 70% accuracy on the classification task. And when we project these 3D images in the 2D, and we do this regular CNN thing, we are getting only 40% accuracy. So that is the main reason. So in case of
how much on spherical? How much on the spherical?
Spherical with 70% accuracy for this data set. For ShapeNet
and epochs.
Epochs we have said no. For this now we have to we run it like 8 epochs or something. I mean, we just save them. We have to do it over some time, right? We keep checkpointing it and we do. So 8 epochs we did. I mean, for both. In case of ShapeNet, we did 8. I mean, we kept everything same just to make sure that the model does not have any sort of leverage over that. So the layers was also same. Again, the same 4-layer network and 4-layer network. We kept that same. So that's how this thing comes out to be. In case of MNIST images, yeah, okay, it makes sense that we are spending like a lot of time into this, but when we go with this 3D objects and this and this complex thing, this trained CNNs are not able to to learn all those things correctly. And also with this particular model, we are getting this additional thing, that rotation invariance. So maybe for MNIST task, it might not be like very much needed, this in rotation invariance, but this is an additional thing that is coming with our network. So that if you are spending additional time on the epoch, we are getting some additional things out of it. I mean, in case of MNIST, it was just to show that even without the data augmentation, these models, I mean, we need not to perform any sort of data augmentation, and it can still perform good. So so ma'am, for this Shrek, and I mean, so this things are now cleared now, so we have to run that experiment again. But we will, I think we'll include all those things in the final report. And also, since it does, I mean, this experiment, and so in the last time in the LA presentation, we have kind of like plotted everything and did everything, but in this thing that it was not, it was not possible to do that actually. I mean, a lot of things were just a pure competition and stuff. So, I mean, it was, so so we did not have much visualization and stuff. So most of the work was like around the theory and setting up the competitions. This was our project, and if you have any other questions or doubts, regarding this project, we can answer.